I've been asked on a number of times to go over this, which is my custom digital clock. Um, People thought that this commentary may be interesting, so I will do it now. The reason this project originally kicked off is because I had one of these as my bedside clock for the longest time. I mean, since, I don't know, 2011, probably, and it was only recently in 2022 or 2023 that I replaced this with my own custom clock. It was not until very recently that I built my very own clock to replace this one, which is this guy right here. Now, I actually have a slightly larger version of this now, but it's functionally the same. So today I'm going to go over my process for building this thing and why it exists. So to start with, let's set some engineering principles or design guidelines, things that are important, things that need to be functional for this clock. Big one is obviously displays. I wanted large displays, something larger than what the Sony clock had, and something a little easier on the eyes. So I settled on these red displays. I think I ordered probably 5 or 10 1.5-inch segment displays. These are just basic 7-segment displays from LCSC. And experimented with these on a breadboard, try to figure out voltage levels, the diode drop, all that stuff, and settled upon these. Following that, I needed some means or some way to drive them, which is 74LS47. You can also use 7447 ICs. These are just binary coded decimal to 7-segment display decoder ICs. They take in 4 lines, A, B, C, and D, and they spit out 7 to drive each segment on the display. The datasheet should show this fairly cleanly somewhere here. I totally went past it, didn't I? Yeah, right here. So pass in a 4-bit number, 0 through 15, and you get out a actual number in decimal at the end. This saves on I/O because I used an ESP32 as the core of this. I used the ESP32S2 because I have a ton of GPIO and all of these are outputs. Some of the earlier ESP32s have fewer pins and have input-only pins. There's only one input-only pin on this, which is, I think, pin 48, 46 right here. This guy is input-only. It's a strapping pin. Same with 0, and I believe 45 is as well. These are the pins to avoid using if you can. So I further challenged myself in this by implementing just the SoC. This is the black package itself for the ESP32. Just the small little guy. It's the ESP32S2. These are like the full dev boards, and I'm going to have to hit LCSC for this. I was implementing just the raw SoC itself, just the little S2 package. What this means functionally is that I need to perform impedance matching on the antenna because I implemented a PCB antenna. So that was the big thing that I was targeting here. I've already implemented a number of different microcontrollers. This is fairly simple. It's just a few pull-ups, pull-downs, filtering stuff, crystal oscillator, of course, and all of the lines. USB data goes on 19 and 20. There's a boot pin. There should be a reset pin somewhere around here, although this early design maybe didn't have one of those. I think I added it later. So then we've simply got a basic voltage regulator. It's just an 1117, super basic input filtering caps, and then the device itself, it takes in 5 volts and spits out 3. We've got our USB port with 5.1 kilo ohm pull down resistors on the CC lines, USB data plus and minus right here. Disconnected these guys because they're not needed, same with the shield. And up here is one of the other big features, which is ambient light sensing. I wanted this thing to automatically dim down in a dark room and automatically brighten back up as it got light out. That way it wouldn't be painful on the eyes late at night, but it was also very readable in the day because that was something that I struggled with the dock. You had to set it really dim, and then if you wanted to actually see it later in the day, you'd have to increase the brightness. So I wanted it to do that automatically for me. Following that, we just have the displays, which are fairly simple. I wasn't sure what I needed to do for these 3 pins, so I just left a resistor so that I could pull them down to ground if I needed to, or bodge in a wire. These are the 4 inputs, A, B, C, and D, and these are the outputs, A through G, which correlate to each segment you can see on the little graphic right here. I have 100 ohm resistors in series with each of these. These are common anode displays, I think, which work out fairly well. Oh, common cathode maybe. It works out very well. These are expensive. You could maybe drive this in a different way, set up a different topology, but this is what I had. 100 ohms are current limiting so that these things don't get too bright and explode, because the diode voltage is somewhere around, I think, 2.5 volts maybe, and this spits out 5 volts. So we're limiting the current that can flow across the diode through this fashion. And we've also got 100 or a kilo ohm on the decimal point, because the decimal point is fewer LEDs and has a lower voltage drop. It's probably 1 volt or something. I don't know the exact details. And this is just repeated 4 times for each of the displays. Finally, the actual dimming circuit is a combination of a PMOS and an NMOS, just like this. So this creates my high side driver. This here is my common cathode. This here is my positive rail for the LEDs. You can see that here on pins 1 and 5. This could maybe be better labeled, but it doesn't particularly matter. So 5 volts comes through this PMOS, which is flipped on and off by this NMOS right down here. So pull this high with these pull-up network right here, which will inhibit current from flowing, or we can use this MOSFET here to pull this gate down to low, which will allow current or voltage to flow through this FET and power the LEDs. By PWMing this thing and flipping it on and off a bunch of times every second, we can cause the lights to dim or brighten, depending on how we drive this. These are filtering caps that were honestly never used. I just left options because I like having options, but they've not been filled, I don't believe. So let's have a look at the actual layout here now that just about everything is together. That's Wi-Fi with the ESP32 and the Arduino framework handled. Makes that fairly easy to work with and do network time stuff. We've got ambient light sensing and brightness detection, USB-C, of course, voltage regulation, and the big thing being the displays. So here is the version 1 PCB. I will do a 3D view because this is easier. This is a 4-layer board because I had to do the impedance matching. So this is the big thing that this board covers. The rest I will go over, but I want to focus on this because this is what my challenge was. This is I believe it's a Texas Instruments antenna for 2.4 gigahertz Wi-Fi, and this is a pi-type matching network right down here. So there's a capacitor, an inductor, and a capacitor. There are then these traces here, which you can see are actually I think they're a strange width, because I have to match the impedance in ohms of these tracks. I think that the ESP32 on this antenna pad here spits out something like 34 plus J5 ohms, and I need to match that to the 50 ohm termination impedance of this antenna here. That's what the resistor or the inductor and the 2 capacitors do. You can calculate this out. I've simulated it on the Smith chart. I may come back and show that. But there's a board stack up that is given by JLC PCB, who was my fab house for this project. You can use the calculator tools here with transmission lines. This would be a coplanar waveguide with ground plane. So you can set epsilon and height, some of these things, thickness of your copper, and compute the width for a specific impedance. So if I need a 50 ohm impedance here. I have an epsilon of 4.6 is I think nominal, and I have 0.2 millimeters between my copper pores and another 0.2 here. I can synthesize a width, I believe. So I need this 0.3355 millimeters, which is pretty close to what this one is. It's 0.349355, so pretty much what I did here. And then you can set the values of the inductors and the capacitors to match the actual impedances. Following that, we've got our decoupling and filter caps. There's also a filter inductor as called for by the datasheet. There's a full technical breakdown, the hardware design guidelines, I think, for the S2 series of ESP32s. It's not this datasheet, it's the ESP32 S2 hardware design guidelines. Yeah, or these guys right here. Oh, of course. Why can I not download this? It was a PDF. Yes. This is an old document. But there's a schematic checklist. You can see that this is basically just the sample schematic. I used the version with built-in flash and RAM because I didn't want to deal with all of this stuff. And it honestly saves me cost. It's easier just to use the integrated stuff as opposed to finding and placing flash and PSRAM. But here's that 2.0 nanohenry inductor that is on the power lines for filtering for VDD3P3. Funny that the VDD analog does not actually have any filtering on it besides a 100 nanofarad. And then there's the crystal oscillator. It's a 40 megahertz crystal. You can throw caps on the side of it, roughly 10 picofarad. You can do the calculation, but I honestly don't. And it's mostly worked out for me. So that is the ESP32. Following that, we have the footprints for the segment displays, which I guess I put on the back of this board. Yeah, I did. Okay. So here are the segment displays, fairly simple. They're just 10-pin devices and they slot in right next to each other. I do have this section of board, this ground plane, removed underneath the antenna so that it can actually radiate power. If you don't do that, your antenna is not going to be functional, and you'll be wondering why. That is why. And then finally, I have got my 74LS decoder ICs in here. So we can take a look and see. I don't know what I ran internally. This is just a big ground plane. This is probably power, looks like. So there's 5 volts that, oh my gosh. There's 5 volts that comes in here from the USB. You can see that my board house must hate me. Wow, this is painful, but whatever. 5 volts comes in, routes through this inner layer here, pops out for the LDO. So we take in 5 volts and linearly just drop it down to 3 volts. It's inefficient, but no problems here. And then our 3 volts comes out to power the decoder ICs because they need 3 volt logic since the ESP32 runs on 3 volts. So you can see that I have my 3 volts distributed out through and around this component. There is finally the itty bitty little ambient light sensor in the back here. I've got my little resistors, which current limit and allow these LEDs to function without exploding. And I've got most of this stuff just connected into IOs. So ton of IO just breaks clean out and then goes across this board, I think on the bottom, or yeah, on the back copper here too. You can see this long trunk just goes out and across. If I switch layers here, you can see it goes into the A, B, C, and I think D pads on the little decoder ICs. And that's largely it. That's the entire clock design. Looks like this right here is where I implemented my backlight stuff. But this was version 1. This is an expensive board. It's like $33 for 5 of these boards because they're 4-layer. And it worked. So I learned what I wanted to learn, which was primarily implementing this matching network and the antenna. If I need to in the future, I can now implement this and copy this schematic over so that I can quickly and easily have a very small footprint little ESP package. But it doesn't make sense for retail sale because it needs to be FCC certified. And this is not. I am allowed to make, I think, 5 of them for personal use, but I cannot then go and sell a whole bunch of them because the FCC is going to get mad. And then if it starts letting off electromagnetic interference, I got to pay a whole bunch of money to have the thing tested and certified and validated. So, enter version 2. I'm going to flip the GitHub repo to the main branch, to be honest. There we go. Nuke out any of my changes and then switch over to main. Which is, this is gone. KiCad no longer exists because the file vanished. So now we're here. And now I've restructured the thing. It looks nicer. So we go into the hardware and we pop open the module-based version. The module-based version is very similar, maybe a little more hectic. You can sort of see that these traces are admittedly not flawless. They could be better, but everything could always be better. So let's go over this one. Right off the gate, the big module is the thing that makes the difference here. This is technically slightly more expensive than just raw integrating the SoC, but this module comes with an FCC certification already, so there's no work needed for me on my end. I've also moved some things around. I put the ambient light sensor in the middle of the board this time. I broke out the JTAG port down here. I have serial RxTX ground and 3 volts broken out down here so that it's easy to debug and reprogram if you would prefer to reprogram it like this. You can also just program it through the USB. I added boot and reset buttons so that you can hold down boot and click the reset button to put it into bootloader mode, which lets you download firmware. You can also hit the boot button to show the IP address of the device. I stamped my new logo on the thing right down here and cleaned up some of this silk screen, which I didn't really show. A lot of stuff's been moved around just to make the layout a little bit easier. You can see that I've used much larger components all around here instead of the tiny 0402s. I think my minimum's an 0603 for these two, and the main current limiting resistors are now 805. This is really just to make it easier for an individual to make modifications if they really wanted to. If they were to purchase this, I've gone very open source for this clock, so all the schematics are freely available and published. I kept the 3 resistors. These are all not populated, they're no pop, but they are there in case anyone wishes to make use of them or finds them beneficial. I don't, but that's okay. I guess I removed the silk, which is sort of unfortunate, and have told JLC to throw the order number underneath this segment display. And that's mostly it. I've just cleaned up this a little bit here to keep the copper away from the antenna on the module. So I think that's the whole thing. I hope that this has been somewhat interesting, somewhat useful, a very fast breakdown. I could probably go into a little more depth here as to the process, but I think that mostly covers it. I wanted a number of different things, and I built this clock specifically to do those things. It's Wi-Fi connected, and really only Wi-Fi connected. You can add an external oscillator here, I think probably in place of the JTAG port, which would make it keep time a little more accurately. You could add an RTC or a quartz crystal, which is the, what is it? It's 32760 something kilohertz. But I have no reason to do that. This connects to the network every day at midnight and refreshes the time, and the ESP module is fast and accurate enough to hold that time for at least a day. It drifts by maybe a second or 2 at most, which is probably unacceptable for some, but more than acceptable for me, given that it's just a bedside clock. It doesn't have to be perfect. So I think that's mostly it. Let me know if you've got any questions, and I hope that this was at least somewhat useful.